All right, so in this video, we're going to talk about what are called functions of several variables. So normally, what we've been doing, we've just had like a function where you say like something like f of x equals 3x squared plus 4, something like that. And we've had input, which was our x variable, and then we've had output, which we would call f of x or y. Okay, so we would plug a number in and we would get a number out. So one in, one out, two-dimensional, right? We had an x-axis and a y-axis. So x-axis and a y-axis. So x-axis, y-axis, and that was it, right? So that's normally what we had. What we're going to do now is we're going to look at functions that actually depend on two variables. So x and y are both going to be our input, and we'll have a third variable, typically z, that will be our output, okay? And what that's going to do is actually graph things in 3 dimensions. So you can think of x and y kind of being the flat part, and then the z-axis sort of like sticking out in the third dimension. So one of the things you're going to be asked to do is find the domain of one of these functions, and all you have to do is realize that the domain is going to depend on both variables. So x and y are both input now. So when you say what the domain is, you have to state what x is allowed to be or not allowed to be, and you also have to do the same thing with y. So if you look at this function right here, I know that I can't take the square root of a negative, so I would say x has to be greater than or equal to 0. And then y is in the denominator, so I would have to say that y cannot be equal to 0. And so the domain is actually in terms of x and y, okay? And then they're also going to ask you to plug numbers into the function. So if they say, what is f of 9, negative 1, they want you to plug in 9 for x, and they want you to plug in negative 1 for y. So if we wanted to do this, then we would get the square root of 9 over, and then for y, we're going to plug in negative 1, and then we have to square it. So we would get the square root of 9 is 3, negative 1 squared is 1. So if we plug in 9, negative 1, we get out 3. So there are several 3D graphers out there on the internet. Desmos has one, but I'm not sure that its output is totally accurate because it's still in beta mode. So I found another 3D grapher that I was using in class today. So I'm going to go ahead and use this one. And we'll come back to this graph right here a little bit later on. I don't know if I can move my screen here. So let's see if I move this over a little bit. I'm going to go ahead and put that function in that I was just talking about. So it was the square root of x on top, and then it was y squared on the bottom. And what it's saying is this is what that graph should look like. So you can kind of tilt it around and do stuff with it, but it is definitely 3D. So you can look at it from underneath, and you can kind of spin it around. And I'm not the best with this grapher, so like zooming out is, not going to look the best. But this is what that graph looks like. So it's like it's 3-dimensional. Okay. You don't have to know what the graphs look like or anything. We are going to do some derivatives with it and stuff, but for right now, what we're worried about is just the notation. So that's the notation there. And then we did this example as well. So what's the domain? Well, if you look right here, x can be whatever you want it to be so far as this function or this part of the function, but you have to remember that when you take the log or the natural log of something, you can't take the log of 0 or anything negative. So x would have to be greater than 0. Y is just in the exponent here, so y can be anything. And the way you say that is y is an element of, that's what this little e is, the real numbers. And so what that means is y can be anything. Okay, so you just say that y is an element of the real numbers. So it can be anything. There's no stipulations on what y can be. And then they want us to plug in 1, 2. So g of 1, 2 would be equal to e to the 1 times 2 minus the natural log of 1. So this is e squared. The natural log of 1 is 0. So g of 1, 2 would be e squared. Okay, that's it. So that's how you plug stuff into a function of several variables, and that's how you find the domain. Okay, so the next thing that we did was we looked at an equation where you would write a cost equation in terms of like two things that a company is making. So if you look at this one, it's saying that the company makes both. So this company actually manufactures two things, which we've never really had before. It makes bicycles that are 3-speed, and it also makes 10-speed bikes. And so if you keep reading, it says let X be the number of 3-speed bicycles, and then it says let Y be the number of 10-speed bicycles. And what it wants us to do is actually write the cost equation, okay? Well, that means that we're going to write C of, now the cost is not just dependent upon X, it's dependent upon both X and Y. So we would say the cost of X and Y is equal to, so 3-speed bikes are $100 a bike. So this would be 100X. And then let's see, 10-speed bikes are 150. So that would be 150Y. And then it says that fixed costs are 2,500. So this is my cost equation in terms of both X and Y. Finally, it says, let's go ahead and find the cost to produce 15 3-speed bicycles and 20 10-speed bicycles. So what we would be figuring out is C of 15, 20. So it would be 100 times 15 plus 150 times 20 plus 2,500. Okay, and that ends up being 1,500 plus, what's that, 3,000 plus 2,500. And if you add that up, to make those, to make that pair, or like 15 3-speeds and 20 10-speeds, it would cost the company $7,000 to do that. Okay, so that's one of the things that you have to be able to do. Okay, there's some practice problems coming up. So what I want to show you is we're going to actually be taking derivatives of this. And so I showed them a couple of different graphs, and we can talk about this a little bit more later because you don't have to actually be able to find these points yet. But these functions actually have relative maxes. They have relative mins, so that guy right there. And they also have what are called saddle points. So this actually looks like a saddle, and actually if I throw it into this grapher real fast, so if I do y squared minus x squared, that's actually going to graph this saddle that you can look at. So it looks like a saddle or a Pringle, but basically a saddle point is this guy right here. So I'll do it on the actual function. It's this point, like sort of right in there. And what it is it is the min if you go this way. So it's the relative min if you go that axis. But then it's the relative max if you go this way. So it's the point where the min going one way meets the max going the other way, and we call it a saddle point. So that's the third type of thing you're going to have to find is a saddle point. So you'll have to find a max, you'll have to find the min, and you'll have to find what's called the saddle point. Okay? So what I'm going to show you how to do now is how to differentiate what's called a partial derivative. Okay? So there's going to be three variables here. And so what a partial derivative is this. When you take, if you have x and y in the function, you're going to be able to take the derivative with respect to x and y, but you do them at separate times. And what's the most important is this isn't going to be dy dx or anything like that. It's not implicit differentiation because there's a third variable. It's not just x and y kind of hanging out by themselves. There's an x, y, and a z. So what we do is we try to figure out what's happening with respect to x, how it's changing, while we're holding y constant. And then we want to figure out what's happening to y if we hold x constant. Okay? Now what that means is when something is constant, it has no rate of change. So its derivative, which is the rate of change, is going to be 0. So I'll show you the kind of notation first. So this is a normal derivative, and this is what a partial derivative looks like. So the d is sort of hooked like that. The kids in class said it kind of looks like a backwards 6. That's the derivative with respect to x. And then the derivative with respect to y looks like that. Okay, so that's one notation, and I'll show you some others. Okay, so you can read through this, but I'm going to show you how to go ahead and find a partial derivative with respect to x. So I'm going to write out what this means. So this guy right here means take the partial derivative with respect to x holding y constant. Okay, so this is a product rule. That's no different. So we would copy the first times the derivative of the second plus the second times the derivative of the first. Now, I didn't take any derivatives. I just put tick marks. Now, remember, at this point, y is a constant. So anytime we have to differentiate y, the derivative is going to be 0. So we can put that here. Y's derivative is equal to 0. Okay, so let's go through and do this. So we'll copy the first. Y is a constant, so its derivative is 0. Plus the derivative of x with respect to x is just 3x squared. And then if you simplify this, you get 3x squared y to the 4th. Okay, so that's called a partial derivative. Now, what we're going to do here is, since we have the y, we're differentiating with respect to y, the partial derivative. So this is the partial derivative with respect to y holding x constant. And what that means is the derivative of x equals 0. Okay, so we're going to do it again. So we'll copy the first times the derivative of the second plus the second times the derivative of the first. Now we're differentiating with respect to y this time, so y is the variable. So x cubed, because we're copying, the derivative of y to the 4th is 4y cubed plus y to the 4th. And then the derivative of x with respect to y partially, right? So we're holding x constant. And so that means the derivative of a constant is 0. So now we just clean this up. We get 4x cubed y cubed. Okay? We did one more example in class. We looked at this one here, and this is taking the partial derivative with respect to x of y to the 4th. Well, y is constant. So if you take the derivative of a constant, because we're differentiating with respect to x, if you take the derivative of a constant, you just get 0. Okay? The homework that I gave them was to finish example 4, and then I showed them another notation. And this is important because this is the notation that Pitt uses. This is the notation that we're going to use. We're not actually going to use, this is called del, like D-E-L. It's like they were writing delta and they just decided not to keep writing. We're going to use what's called the subscript notation. So these are the same thing. So the derivative with respect to x. So the partial derivative with respect to x in subscript notation is f sub x. And then the partial derivative with respect to y is f sub y. So what this says right here is take the partial derivative with respect to x if this is the function. Okay, so you're going to take the partial derivative with respect to x of this function. Okay, so you need to go back and do example 4, and I'm going to do example 5 with you right here. Okay, so I'm going to take the partial derivative with respect to x of this function. Now you got to be careful right there because you have a product rule with subtraction. So f sub x, so we don't have to do this d anymore. Okay, we could just write f sub x is equal to the derivative of 5x to the fourth with respect to x, because y is the constant, this would be 20x cubed, minus, and here we go, we have to do a product rule. Copy the first times the derivative of the second. The partial derivative of y with respect to x is 0 because y is constant. So copy the first times the derivative of the second plus the second times the derivative of 2x squared with respect to x is 4x minus the partial derivative of y with respect to x is 0 because y is constant. And so if we clean this up, we get 20x cubed minus 0 minus 4x y cubed. So that's the partial derivative with respect to x of that function. In this question, they're asking you to do both the partial derivative with respect to x, and then they're asking you to start over and do the partial derivative with respect to y. So far you should do example 4, you should do example 6, you should do example 7, example 8, example 9, and example 10. So you should have those all done for tomorrow. If you need some help, you can sign up for PLT. We have a little bit more to do because we have to do second order derivatives, and then we have to figure out how to find relative extrema.